All right, let's jump right in. We're going to follow a recipe today, but it's a little different. We're going to try and make something you can actually hold in your hand, completely out of thin air. And trust me, this little thought experiment, it's going to totally change how you look at the world.
Yep, you heard that right. A banana. Could you really just grab all the atoms floating around in the air and, snap them together into a banana? Now, it sounds like something straight out of sci-fi, I know. But the amazing thing is, this whole idea is actually based on real science. It's just, well, we're going to push it to some absolutely absurd extremes. Okay, so let's get into it. Step one for any recipe, right? You got to know your ingredients. So before we can even think about building a banana, we need to know what a banana is actually made of. I'm talking all the way down to the atomic level. We need the blueprint. So if you take a regular medium-sized banana, it's mostly just three things: carbon, oxygen, and hydrogen. I mean, that's the vast majority of what it is. Then, of course, you've got smaller but super important stuff like potassium. That's what everyone knows bananas for, right? Plus a little bit of nitrogen, and then just tiny traces of other things. So there it is. That's our shopping list. These are the atoms we've got to go out and find.
Okay, we've got our list. Now let's see what we've actually got in the pantry. And our only ingredient is thin air. So, what can we pull out of the atmosphere? And yeah, this is pretty much where our problems start. Big time.
So, the air all around us, it's almost all nitrogen, like a whopping 78%. Then you've got oxygen at about 21%, and the rest is pretty much just argon. But you know what's really wild about this? It's what's missing. That carbon we need so badly, it's all locked up in carbon dioxide, which is, get this, a tiny, tiny fraction of 1% of the air. Not a good start.
And here's the core of our problem. The mismatch is huge. Let's say we filter 1 million liters of air. That's about the size of a small house. We'd end up with an incredible 9 kilograms of nitrogen, but only 1.5 grams of carbon. Now look at our banana recipe. We need less than half a gram of nitrogen, but we need 48 grams of carbon and 8 grams of hydrogen. It's just, we are absolutely swimming in nitrogen we don't need, and we are starving for the carbon and hydrogen we do.
This chart really just hammers it home, doesn't it? This is the carbon problem, plain and simple. To get just those 48 grams of carbon for one banana, we'd have to process more than 30 million liters of air. It's a staggering number. And it's kind of a fascinating flip side to climate change when you think about it. That tiny amount of CO2 is enough to warm the whole planet, but it's a completely terrible source if you're trying to collect raw carbon. So yeah, just harvesting it from the air, not gonna happen. We need to get a lot more creative.
Okay, so this is where our little recipe gets really fun and completely impossible. The idea is if we can't find enough of the right atoms, well, we'll just have to make them. We're going to take all that nitrogen we have way too much of, and we're going to change it into the carbon and hydrogen we desperately need. There's a word for this. It's called transmutation. Basically, modern-day alchemy.
So we've got 3 options on the table, and let's just say they're all pretty ambitious. Option 1 is nuclear alchemy. You use a giant particle accelerator to literally smash atoms and knock protons off, turning them into different elements. Option 2? Oh, we could just build a miniature star and use its fusion to cook up the elements we need. No big deal. And option 3 is straight out of Star Trek, a replicator that just rearranges all the subatomic bits and pieces however we want. Simple stuff, right?
Yeah, not so much. Let's put this in perspective. Let's say we could use a particle accelerator, and it worked perfectly, 100% efficiency. The estimated cost, just in energy, to create the atoms for a single banana would be around $7 quintillion. That number is so big, it's basically the entire GDP of planet Earth for one banana.
But okay, let's just imagine for a second that money is no object. We've just spent the entire planet's GDP. And now we have this perfect little pile of all the atoms we need. We're not done though, not even close. In fact, you could argue the hardest part is just getting started. Now, we have to actually assemble the thing. See, a banana isn't just a random pile of atoms. It's this incredibly complex, beautifully designed molecular structure. I mean, look at this list. We'd have to build simple sugars like glucose and fructose to make it sweet. Then we'd have to link thousands of those into long chains of starch. We'd have to literally weave cellulose and pectin to make the peel, build complex proteins, vitamins, and we'd have to fold every single one of those molecules into a perfect 3D shape. We'd even have to build the stuff that gives a banana its flavor and makes you feel good. Every single atom has to be in exactly the right place.
This quote from the source material just sums it up all so perfectly. It's the beautiful absurdity of this whole project in one sentence. Capture, transmute, then use a room-sized molecular assembler yielding one edible banana. It's the whole impossible recipe, right there. It sounds so simple, so elegant, and it is absolutely ludicrous. So, after all of that, after we've built a star in a jar, spent the entire world's GDP, and designed a molecular assembly line the size of a factory, you gotta ask, right? Is there an easier way to do this? And well, as you've probably figured out by now, the answer has been staring us in the face the entire time.
And there it is. That's the punchline to this whole crazy thought experiment. In practice, the simplest, most efficient, and, yeah, infinitely cheaper way to make a banana is to just plant a banana tree.
You know, nature figured this all out millions of years ago. It's called biology, a banana plant. It uses photosynthesis to just grab the carbon it needs right out of the CO2 in the air. It pulls water and minerals like potassium up from the soil, and it uses free energy from the sun to power its own perfect little molecular assembly line. It solves the carbon problem, the transmutation problem because it doesn't need to do it, and the assembly problem all at once for basically free.
And really, that's the whole point of this explainer. By walking through this absurdly complex, ridiculously expensive process to create something as simple as a banana, we get to see the true miracle of the natural world. It really makes you wonder, doesn't it? If a single banana is this miraculous, what other everyday miracles are we just completely overlooking, hiding in plain sight all around us?